I'd like to introduce our next speaker. His name is Javi, and he'll be speaking about his company and his journey going through using Azure Cosmos DB.
Hi there. Thank you. Okay, so let's get started. Hi, everyone. Good morning, good afternoon, good evening, and welcome to my session. I hope you're enjoying the conference so far. My name is Javi Velasco, and I work as an API engineering lead at Vercel. In case you're not familiar with what Vercel is simply the fastest way to deploy front-end applications. We enable collaboration by giving front-end developers comprehensive tools to build high-quality websites. Our mission is to help build a better web. With Vercel, you can connect a repository through a Git provider and instantly generate multi-cloud deployments that are globally available through our Edge network with every Git push. We have been using Cosmos since 2017 as our main persistency system, and it has been a really big part of our history since then. Being our main persistency, we have had a very intensive usage of it for both our APIs and the Edge network. And in the case of the Edge network, latency is especially critical, and Cosmos distributed nature has been a great fit for it. During all of this time, Cosmos DB helps us scale tremendously well from just a few million requests per week to more than 10 billion requests a week that we're handling today. Overall, we are currently making more than 1.7 billion requests a day to the database, and that's all scaled smoothly, keeping always a very good latency. So in this talk, we will see how we used Cosmos at scale in Vercel to work in a very performant way. And there is no better way to illustrate the journey that we have had with Cosmos than walking you through the wrapper that we have built on top of the Node SDK to optimize our access patterns. It started as a way to put together some code patterns that we required on a day-to-day basis, but later it evolved into something more complex that helped us to use Cosmos at scale and to solve problems that you might be facing today as well. This is a talk that I expect to be very useful for developers. We are running a lot of API services on Kubernetes, making an extensive use of TypeScript and Node.js, and of course, Next.js. If you're a developer working with Cosmos and these technologies, I'm pretty sure you're going to find this useful. Nonetheless, I expect you to find it interesting as well if you are a DevOps, SRE, or if you're interested in these technologies. So we are going to divide this talk into a few sections that can put together some of the features that we have been building over time. We will start by defining the reason why we have an SDK wrapper. And then we're going to quickly take a look into our observability tooling, which includes some primitive features that we've introduced back in 2017 to more recent and sophisticated tracing metrics. Next, we're going to see how we improve performance and reliability with some middleware-like features for our Cosmos calls. And then we will see how we enrich our data models, introducing a configuration layer that has been pretty much the cornerstone to more advanced tooling. And finally, we will close with some slightly more complex tools that we created to optimize access and guarantee cross-partition uniqueness of certain values that we called secondary keys. Finally, we will introduce a feature we call mirroring that helped us a lot when it comes to repartition collections. So let's get started. Why a wrapper, right? This is a typical scenario of any application that is using vendor libraries or SDKs. You're in control of your software, but not really in control of the libraries. It's true that you can browse them, you can fork them, you can PR, but you can't make changes that are specific to your domain. Forking is usually not the best idea if you want to keep leveraging maintainers' patches and updates anyway. So this means that you are in the end not really in control to do whatever you want to do with that code. And in our case, we have plenty of services that are using the SDK directly. So we would be sold to these places, to these future changes with this model. We have to also consider that there might be cases where you want to add some extra processing layer to each SDK operation. So it is for this that we wanted to transition from this model to this other model. We would have an adapter between our services and the SDK, and that's going to dramatically reduce the amount of places where we have to make changes in the events of an SDK breaking change. We already lived this when we went through some major updates of the SDK. For example, when Cosmos 3 was released, it was shipped with some breaking changes optimization that we could very easily leverage with a very small effort, since we just needed to change our adapter. Another huge benefit of this model is that it makes very easy to inject layers and behavior on top of every database call. That is why, that is why we adapted every single Cosmos call to include layers that bring, amongst other things, observability. Our observability pipeline includes very simple tooling like logging, stats-D metrics, both introduced in 2017, and also includes some more complex tooling like tracing, which we implemented using APM. Now that we know that every single SDK wrapper is wrapped, we can introduce how we plug in these features. So assuming that you can generalize the contract of every Cosmos call to a lazily evaluated function that would end up resolving a response or a feed response, we can create a composition of higher order functions that would be adding layers with very specific behavior to every SDK operation. For example, in this case, in the snippet, what we are doing is bringing observability through two decorators. One is with stats emitter that would receive an event emitter through some provided configuration, and the decorator would use it to publish events with metadata. For example, it would tell how much time an operation took, what is the query that it ran, time taken, cost, etc. With logging is a much more easier one, and the responsibility would be to simply log a line to std out before and after the operation happens. This log is going to be alerting on the cases where it becomes very slow or there are expensive queries or failures, so we can relate stack traces in our logs to potentially harming Cosmos operations. The stats emitter in particular was very useful because it allowed us to have a complementary panel in our observability pipeline that is showing pretty much the same as the Cosmos usage panel is giving in the portal, but with a very important difference, which is that in this case, we can define very fine-grained alerts when it comes to root consumption. For example, if it's going above a certain limit, we can set an alert, or if we have a very expensive or slow operation, we can also trigger alerts. Nonetheless, this is still working on top of the SDK request, but not from the requests themselves. So we are still blind and we don't know how much time is being spent on the SDK, how much time is spent in our wrapper, how much time that request actually took. So it is at this stage when it became very useful, a new feature that I think it's still undocumented in the Node SDK, which is the plugins that is going to allow us to define for real a middleware where we can execute code before and after every single request happens. So we defined a tracer plugin that is going to work through APN and would start a span as soon as a new request happens and close it once the request is done, tagging and logging all error and all sort of useful information. Now, what is very interesting about this is that if we also trace our wrapper functions and the SDK functions, we can finally have a flame graph per operation that is going to show a timeline telling how much time each operation took. In this case, we are looking at a modified document by ID operation there in blue that we will see later. But for now, it is ignored by checking that it's doing two operations under the covers where the request is taking most part of it, but not all of it. This level of information has been proven to be of an enormous value since it is extremely easy to find slow requests and bottlenecks and errors. At this point, technically, we could go and to our previous decorators and replace them. But it's not really like subtracting value using these plugins because there are still some features that we worked out in order to improve performance and reliability, for example, that are relying on the same pattern. So for performance and reliability, we followed a few strategies that are complementary to each other, and they are implemented in several different ways. The first one is adding a retry and a semaphore layer in order to improve our reliability on every Cosmos operation. As you can see in the snippet, they work in the exact same manner as the stat emitter and the logger that we have already seen. With retry, is going to give a retry strategy for errored SDK requests. Now, since 2017, the retry logic in the SDK improved a lot, and there is no strict requirement to have a custom retry layer for network errors anymore. But there are still some cases where the SDK request can fail, but still be retriable. For example, when the write session is not available. This has been very useful for such cases. We also have a layer that adds a semaphore in front of all of these requests. And this is going to help us making sure that we don't take the event loop. It helps controlling the concurrency, how many operations are going to be running at the exact same time. If we do, for example, a promise all with thousands of operations at the same time, we will make sure that we are not taking the event loop and we are not running a lot of operations in the exact same millisecond. With this, we complete all of the decorators that we have in front of every single operation, but there are more interesting things that we did to improve performance and reliability. In our experience, when we are reading a document and that is taking more than half a second, it usually times out. This has to do with the Cosmos gateway being too busy, and usually a simple retry is going to help in this case. We have seen it in our observability pipeline, many cases where a request took exactly the timeout that we have set plus 1 second back off plus a few milliseconds. And this is precisely because the very first retry is going through correctly. So a good strategy to overcome this issue is to have an early timeout strategy for the first try. That timeout can be increasing with the next retries, but it is very important to know that it has to be tied to each operation. For example, reading a document is not going to take the same amount of time as a query, so we can be that optimistic. It is for this that we defined a plugin in a similar way that we have seen for the tracer that allows to pass a times out policy to our wrapper, where we can specify not only the timeouts that we want to get in a sequence, but also the amount of retries and the backup strategy for each of those. This has been very, very useful for us, and it helped reduce dramatically the max time and the P99 in our APIs. Another one that is one of my favorites when it comes to reliability in our system is the ability to perform safe updates, avoiding race conditions and potential data loss. In systems where we are processing, like in ours, thousands of requests per second, and we have spawned jobs that are processing and accessing and mutating the same data concurrently, there is a very high risk of overwriting data because of race conditions. Say that you have this scenario where you are reading a document and then you update the document locally and then you push the mutation to the server. The chances that the item was modified by the time you push are very high and can lead to data loss because you are updating stale data into your system. REST APIs solve this with versioned resources using e-tags, and Cosmos works exactly in this way. So we wanted to bring this behavior to every single API, every single place where we were pushing changes for a document, and retry in case we got an error with the e-tag. So we modeled this high-level tool, modify document by ID, that would help us in those scenarios. It works just by receiving the collection name, the document ID, and an updater function. So what it's going to do is it's going to read the document by the ID or the information that is provided, and then it's going to apply that modifier updater function. If it performed any changes, it's going to push the change. And in case it fails because of the e-tag or the resource version, then it's going to retry and apply the function again. This was really, really helpful for a use case, and it helped us to be super sure that we are not getting into this trouble of overwriting data with stale data. So now let's see how we enriched our models and brought a declarative way to express what our collections look like. In this section, we're going to see how we define features that are present in other databases and are essential to operate Cosmos in production, in my opinion. The first and most important of those is timestamps. There are many databases out there that have out-of-the-box support for timestamps. Those are going to tell you when a transaction took place, when a document was created, when it was last updated, and in some cases when it was deleted. So since we have this SDK wrapper that runs on top of every single mutation and operation, instead of going to every single place and add these fields to different documents, we can just put it in our wrapper. And it is worth mentioning that this is very useful for sorting information, so sorting records depending on when they were updated. And Cosmos includes already an attribute for this, but you can opt out from updating that attribute when you push an update to a document. And we wanted to have that feature, which is why we implemented this. Another one that is very closely related to this is soft deletion. We never remove data for real. What we do instead is that we store a timestamp that is going to tell us when an item was deleted. The reasons why we have this is actually very obvious. Removing data for real is very risky. And in case that you are rolling some regression or some buggy code, you don't want to just remove data in an unrecoverable manner. In the snippet, you can see how we usually remove documents. We just set a timestamp through a wrapper function, and from that point on, we are going to ignore those documents. Of course, this comes with a cost because every single query is going to have to include automatically a predicate to leave all of these records outside of every query. Of course, this behavior can be opt out. And this doesn't mean that we are keeping records forever and ever around. We have some pruning processes that are going to be removing data after a safe period of time, depending on the entities that are going to be cleaned up. So another thing that we didn't mention just yet is partitioning. In Cosmos is very important to partition collections correctly. And it is something that obviously we didn't do at the beginning. In our wrapper, we automatically use the ID as the partition key because all of our collections were partitioned by ID. So when the time came that we have to use a different partition key, the wrapper just didn't know how to inject the right partition key. So we decided to create a very simple configuration object that would enumerate all of the collections that our system has and what their partition IDs were. This enabled us to do very interesting things aside from injecting the partition keys automatically. In the snippet, you can see how we are just enumerating collections. We're going to be referencing later those collections rather than hard coding the strings, and we can define their partitions. On the case where we have a configuration object like this, and we are running a cross-partition query through a helper, what is going to happen is that we can analyze the query, and we can see if the partition key is actually being included in the query. With the SDK version 3, if the partition key is included in the query, it's going to work in a very efficient way. But if it's not, it's going to be doing a cross-partition query. And that is going to be a very costly operation. So we wanted to make developers very aware of this fact and force everybody to into the awareness of making cross-partition queries. So we have managed to use this configuration in a way that it throws a synchronous error if you are running into a cross-partition query without specifically telling so through a flag. This helps us save a lot of cross-partition queries. And related to this configuration, everything fell into place when we started building a testing framework that would use our in-memory replica of the Cosmos DB server. That link that you're seeing there is public, and you can access and use it today. It is a Cosmos DB server that works in memory, and it has pretty much the same API as the one you use in production. So in order to set up this server, we obviously need to create containers, create user-defined function, composite indexes, and so on. Because we already had a configuration for the wrapper with all of this information, we just needed to enrich it a little bit in order to generate the database server that is suitable for our schema. Even though those properties like unique keys and composite indexes are not really used inside of the wrapper, it becomes very handy to have them around because you can just have a look at your configuration and have a very high level view of what the schema looks like, and that all respecting the schema free and flexibility of the Cosmos database. So this was an incredibly useful feature for us. In our testing pipeline, we have this in-memory server that boots, clears, and then self-configures automatically for every single test. From this point in time, testing became a matter of creating a bunch of documents to reproduce a scenario, run the code, and then run the assertions. And we didn't have to think about setting a server anymore. As a matter of fact, this gave us the idea of a feature that we called database snapshot testing. So based on the configuration, it would be very, very easy to have a function that would go through every single collection, querying all of its information and creating a sorted object that you can use to retrieve the whole state of the in-memory database. So that way, testing becomes a matter of preparing the environment, doing a get on this whole database state, and then running the effects, getting the state again, diffing, and snapshotting that everything is working as expected. It is a very handy way to test side effects. So the next important feature that I want to talk about is that what we call secondary keys. And this is one of the most important that we have faced in our journey with Cosmos. This was crucial for us to minimize the amount of cross-partition queries and to ensure unique values across different collections and partitions. Say that you have a model like this with users and teams. The user is going to hold some data that in a relational database would be primary keys, like values that are unique to the system and can be used to index the entity. On the other hand, you have a team that also has a couple of keys, like the ID and the slug. Now, what is interesting about this use case is that we want the username and the team slug to be in a shared namespace. We want them to be unique, even if they are documents stored in different collections. Besides that, we need to have an optimal access to users and teams using their unique values. When we choose the partition key, we would say that it is the ID in these cases because it's the most common access pattern. But still, we're going to have many places where we need to find a user by email, for example, and that's going to be a cross-partition query that over time can be very, very damaging. So how do we solve this thing? This is why I said that the configuration was like the cornerstone of this advanced tooling. We just added some configuration values that would tell what are the secondary keys in our system. For example, for users, we will say that the key email and the key username are going to hold secondary keys. And we will say what is the collection where we want to store what is going to represent the key. Then optionally, you can also give a namespace to make sure that you can have living keys in the same namespaces that would collide with each other to ensure uniqueness across usernames, and slugs in that case. Of course, when we run now create document, the downside is that we are going to be creating not only one document, but also documents for the keys themselves. Those keys are going to keep information about the original collection, the original partition key, the original value, etc. So what is really great about this thing is not only that it is allowing uniqueness, but also when we get a document, we can have a helper that is going to get documents by keys or no. You can simply tell what is the collection that you are accessing, what is the key that you want to access, and what is the unique value. And instead of doing a cross-partition query to retrieve that value, we are going to do 2 consecutive get documents by ID that can be up to 50 milliseconds, which is much, much, much better than a cross-partition query. Of course, there are still 2 reads, but I think that the balance is pretty good overall. The most challenging part about this is that we had to model sort of transactions. We don't have transactions like we mentioned around this morning. So we had to be very careful when modeling this to make sure that if there is a failure, we could roll back the changes that we already done and we don't leave stale data. Still, we left some other tooling in place for reindexation and to make possible eventual consistency and self-recovery. The last one that I really want to briefly just mention is mirroring. Since our collections were not correctly partitioned from the very beginning, we had the need of switching them at some point. So in order to figure this out, we added some more configuration that would tell that a collection has to be mirrored into a different collection. And when any mutation happens, creating a document, modifying a document, anything, the outcome would be published to this other collection. So as soon as we roll a new version with this configuration of our SDK, of our wrapper, everything is going to be populating automatically. So the only thing that is left is just to run a backfill function that would create all of the remaining items, going through each of the items in the collection into the new collection with the right partition. Then we reach the point where we have one-to-one documents between both collections, and the only thing remaining would be to switch reads to the new collection. This was very, very helpful, and it helped us to correct our data in production without downtime and remodel our collection. Of course, there is much more to this. It's a very condensated talk, so feel free to reach out and discuss ideas and any other questions you might have. And if you want to help us build a better, faster, more scalable web, we are hiring. So reach out to vercel.com/jobs or ping me directly in Twitter at Javi Velasco. My DMs are open. Thank you so much.
Thank you so much, Javi, for a great talk. I really liked how you really focused on how the wrappers help when there's changes upstream done to the SDK and you want to kind of protect your users and protect your apps and decide how you want the change to go downstream to your applications. It gives you a lot of flexibility that way, and I thought that was really cool.
All right, thank you.
One question we got from our users was, are there cases where you don't want to use wrappers, where it's not worth doing so because of performance or some other reason we're not thinking of?
Right. I think that in general, in every API that is out of your control, but not necessarily just tooling, but more like SDKs. For GitHub, for example, and other Git providers, we are also having like our own clients that sometimes are relying on their SDKs and sometimes are just doing raw request. In those cases, if some new change comes, some new API, experimental API comes in, we don't even have to wait for them to roll those into the SDK. We can just go and implement it our own. That is very cool. Cases where we don't really need this, I guess that if you are using a library that is very lightweight, like for example, if you are using in Node.js, would be something like Lodash or Lambda or something like that, that is very, very minimal. Those cases, they are just helpers. So there is no really actual value in having a wrapper on those.
Okay, great. So it sounds like assessing the value is kind of like a balance between, are we getting any benefit out of putting this layer between for our users?
Yeah, and the primary one, the most important one, I would say, is observability. If you have a synchronous function in JavaScript, for example, there's no need to observe that usually. Depends on the size and what it's doing, of course. But if you are doing under the covers on network requests, like for example, something that we have found very valuable is that the SDK is doing its own retry strategy under the covers. So if we just wrap it and we just trace that, we are going to see in the end how much the SDK call took, but not how much the request took. So that is why these plugins were very, very useful. And this actually extends to other SDKs. You can maybe disable the retry strategy if you are not so sure about it, and put your own in front of it, where you can also instrument proper observability. So I think that's very helpful. Yeah.
That's great. That makes a lot of sense.
Just Sorry, one more question. Thanks so much, Javi. I really enjoyed this presentation. Definitely a model, a model partner here on how to use all of the functions, all the things we have available. Quick question. You mentioned that for partitioning, you had the wrong partitioning strategy. How important was observability in diagnosing, hey, maybe I have the wrong partition here?
Oh, that is a very good question. Thank you. So once we have the observability is when it actually started popping out. The first thing that we have seen back in 2017 was that when we were running cross-partition query, we added this wrapper that was just the logger. That was a very naive implementation. But then we visited the logs of a very critical service. And for every request, we have seen like thousands of log lines. So that actually revealed that there was an issue there. We are using an access pattern that is very required to be fast and optimal, and it was really terrible. So that is one of the ways that we discovered that. Then when we got something more sophisticated, it was even more explicit because you can actually see the flame graph showing you a lot of tiny slots with every single request that it is doing under the covers. So observability was super important for that. And this solution that we came up with, the secondary keys, was very, very helpful, especially in our dashboard when fetching users. We had very common use cases where we needed to fetch a user by email while the email is not the partition key. So how can we do that, ensuring uniqueness and ensuring that it works in a very fast and efficient way? It was very difficult. And in a previous talk, it was mentioned that since you're lacking transaction key because you are using a nosql database, you have to implement our own kind of transactions. And that was a very challenging part, but it's definitely worth it.
Okay, awesome. I actually had a bunch of questions, but we're not going to have time for me to ask them. So maybe I'll reach out to you, Javi, and I'm sure others will as well. There's some really cool features that you built there, so that's awesome.
Thank you.